Nobel laureates in physics and chemistry, laureate in economic sciences, your excellencies, members of the Academy, ladies and gentlemen. So nice to see so many of you here today. Everyone is born curious. This is what makes humans interesting. The more we understand, the more we want to understand. But some of us keep a desire to see and understand which goes beyond most of us, and use their curiosity in an ingenious way to explore and discover all the magic things that our world is full of. Albert Einstein said, "I have no special talents, I'm only passionately curious." I don't believe that. To achieve what he did, and what this year's laureates did, curiosity is certainly needed, but not sufficient. Talent is also needed. Curiosity means asking questions and being prepared to receive any answer, not just the one that was expected. What characterizes the creative mind is the ability to identify the questions that lead to new discoveries and to come up with ways to find the answers. This is how we expand our knowledge about ourselves and about the world we live in, how we improve the conditions for our lives. Man has made and used tools ever since Prometheus stole the fire from the gods and showed us how to use it, in order to manage everyday life, as well as to enable new discoveries. The way humans make and use tools is perhaps what sets our species apart more than anything else. When new bold questions are asked, available tools may not be sufficient to find the accurate answers, but new tools of ever-increasing complexity may be needed. This requires not only scientific excellence, but also technological skills. New tools and new methodologies have taught us about the secrets of life, allowed us to look into the world of the tiny constituents of the cell responsible for life. The highly symmetrical and beautiful agents with ability to attack all forms of life. They have told us about the history of the universe, closer and closer to the origin of everything. As expressed in poetic form by Harley White, Ligo's antenna have finally disclosed those gravitational waves Einstein proposed that travel along with the swiftness of light and can't be obstructed in their spatial flight. Miles of steel tubing in L-shaped position of vacant chambers used in the mission for gauging expansions and fluctuations with an outcome exceeding expectations. These are certainly great achievements which have largely contributed to our understanding of how life works and how the world came about. But to understand the behavior of human beings is at least as complicated. There are no natural laws to lean against, since humans are equipped with limited rationality, social preferences, and lack of self-control. We pray, and lead us not into temptation, but deliver us from the evil, but are trapped by the 7 deadly sins, by greed and gluttony, and by a desire to acquire and possess more than one needs, to constantly make questionable decisions and not change the behavior. Alfred Nobel, he recognized the importance of science and those who uncover what has been hidden, who explain our mere existence, who improve the quality of our lives, who open doors for future finding. This week is the big celebration of science, and today you are all welcome to listen to the laureates who have widened our understanding of the world we live in and of ourselves. I will now ask Professor Nils Mårtensson, Chair of the Nobel Committee of Physics, to present the Nobel Prize in Physics.
Okay, most welcome. My name is Nils Mårtensson from Uppsala University, and I'm the chairman of the Nobel Committee for Physics. And it's my great pleasure and it's a great honor to introduce this year's Nobel laureates in physics. So, more than 1 billion years ago, two black holes merged far, far away. And they created gravitational waves, ripples in space-time, which travel at the speed of light through the universe. On the 14th of September 2015, these waves passed Earth, and they were then captured by the Ligo detectors, producing the signal you can see here. And in a fraction of a second, it was all over. This is an incredibly weak signal, and I'm still amazed that it was possible to detect these at all. And gravitational waves were predicted by Einstein 100 years ago, but it is only now they have been detected. And with this remarkable achievement, we now witness the dawn of a new field, gravitational wave astronomy. And this crowns efforts by a large and international team of scientists and engineers within the Ligo and Virgo collaborations, and which has been going on for several decades. At the same time, you can identify individuals without whom this would not have happened. And today's Nobel laureates also represent in an excellent way the diverse competences needed for the success of LIGO. So today's laureates are Rainer Weiss, the Ligo-Virgo collaboration, and the Massachusetts Institute of Technology. Barish, Ligo-Virgo collaboration, and California Institute of Technology in Pasadena, California. And Kip S, Thorne, Ligo-Virgo collaboration, California Institute of Technology, Pasadena. And they get this award with a citation for decisive contributions to the Ligo detector and the observation of gravitational waves. And with that, I call the first speaker to give his Nobel lecture, and that is Professor Rainer Weiss. Professor...
Well, this is a pleasure to be here. But before I start, I want to acknowledge that the three of us wouldn't be here at all if it weren't for people who are in the LIGO laboratory, in the LIGO scientific collaboration, and in the Virgo collaboration and the Virgo experiment. And since some of you are here, I'm going to insist that you stand up. Would you please do that? They are really the reason we're here. Now, The three of us are going to give a talk which on the surface looks the same. You saw the titles, LIGO and Gravitational Waves. And I'll give you a little preview, and we won't really be able to hold to this preview exactly. I'll talk about the old times. I'm the oldest. And Barry will talk about the present, and Kip will talk about the future. Now, it's not going to go quite that way, and we will intermingle the times, so don't forgive us. But that's the basic structure. So let me start by those of you who don't really know much about gravitational waves and gravity. This is mostly a little bit of a pedagogical thing in the beginning. As most of you were trained in high school and possibly in college, is you learned about Newton's theory of gravity, which is a theory in which there are forces between masses, and that force gets smaller the bigger the distance between the masses. And it is a wonderful theory. It does almost all you need. In fact, it got the space program working. There's nothing terribly wrong with that theory, but it isn't right. Okay? And Einstein saw this pretty quickly. After he developed the special theory of relativity, it doesn't have a way in it of dealing with very large masses moving at high velocities. That's not in Newton's theory at all. And nor does it have a way of communicating information in the gravitational field from one place to the other. For example, if the sun disappeared, and we know it takes about 9 minutes for us to see that, it also should take something like 9 minutes for us to find out gravitationally that something has happened to it. And that's something that, again, was not in the Newton theory. And so this picture, which is hardly complete, but is some way to imagine this new theory that Einstein developed, is if you imagine a jungle gym, a big assembly that you played in as kids in New York, where I was, there were lots of those, and you take a cut through it, and you have laid out all those bars, and you've done one more thing, which isn't something you did when you were a kid. You laid clocks out on every intersection point. All along here, you put clocks everywhere. And what the Einstein theory says is what this picture is trying to show. If you take a cut through it, there will be, when you're far away from the sun, that's the sun, and when you're far away from the Earth, when you're far away from those, let's say out here, space itself looks very Euclidean. It looks the same way as the jungle gym did. And the clocks that are running on all those intersection points, they all read the same time. But as you walk toward the sun in this plane, you'll notice that the distortion in space. You don't see the distortion in time because I didn't put your clocks there, but the clocks in here are running a little more slowly than the clocks out there. And a little bit of that also happens at the Earth. There's a little dimple that the Earth does. And the way John Wheeler explained Einstein's theory, he says, matter distorts space and time, and then matter moves because of the distortion in space and time. And that's the best I can do for you. Kip will do better, okay? And in that theory, there is also gravitational waves. And I want to show you first the gravitational wave. The gravitational waves move at the speed of light. You've heard that already. But they are, as you'll see in a minute, and what this picture will show, is they're a transverse wave. They're a wave that distorts space perpendicular to the direction in which the wave moves. And so let me turn on this little animation. But before I do that, because you'll get sick looking at it, there you are right there. That's you in that little red square. And now I'll turn on this animation so you can see the wave coming by you. And you'll see some patterns in this which are important for understanding how we detected these things. First of all, you'll notice that in, let's say, the horizontal direction, let's say it's expanding, but in the vertical direction it's contracting. Now, any one moment, these things will flip, but they will be opposite motions vertically and horizontally. That's one thing. So that's a pattern that you exploit. By the way, you'll see how we exploit that. The other thing about it is that these are objects that you threw out into the space as the gravitational wave comes through. I should have told you that. So you look here near you, let's say these little masses, they don't move very much. But the masses that are far away from you, they move a lot. And that's a picture of a constant strain along at any one moment. The change in distance between objects is proportional to their separation. And that change in distance divided by the separation is called the strain. And we will talk about that a lot. That's the quantity we measure. Well, we actually measure the distance separations, but the quantity you describe as the field quantity in the theory is the strain. And so let me tell you a little bit of history now. We talked already about this theory being developed about 100 years ago. In 1915, Einstein gave the world the general theory of relativity, which was described somewhat by that first picture. But then, in 1916, he wrote a paper. I'm going to have to drink something, just to bear with me. It's not forever. Yeah, what happens is that in that theory, later on he had a paper in 1916 where he describes a lot of things that showed that it had a Newtonian limit. And he also shows that there are gravitational waves in that 1916 paper. And the only reason why I bring this up here is because of a very interesting statement he made at the very end of the paper. He's described these things. Now, I'll talk to them about them in a minute. But he describes an equation which is up here. I will only tell you what that is. It says this is the strength of gravitational waves, and this is the source of gravitational waves, oscillations and accelerations of matter. And he says something extremely interesting. I have it here in German, but I'll read it to you in English. In any case, one can think of A, that quantity, will have a practically vanishing value. This is at the end of that paper. It says you'll never be able to measure this. It's of no consequence to science. That's effectively what he was saying. And so he makes a mistake in this paper, but that has nothing to do with it. In 1918, he corrects that. But I'll be presumptive a little bit. And I've asked the people who will have the Einstein papers to try to find what I'm about to show you. And they haven't found this on the back of an envelope or in his notebooks. But I'm sure it's there somewhere. So I'm trying to give you a little feel for why he made that statement. And you have to put yourself in the context of 1915, 1916. What did people know about, and what did they have? And the first thing Einstein might have thought about is two trains colliding. How much gravitational waves come out of that? And so let me give you, this is not, no, it's only formula, but I'll explain it to you, okay? So here's the strain, that's H, and this is the quantity that when you want to estimate how much strain you get from some kind of motion, it's a very simple estimation formula. It has the Newtonian constant in it, the mass of the objects, and the distance you're away from them, and the velocity of light squared. That quantity, gm divided by rc squared, is a very important dimensionless quantity that we all know and love. What it is, on the Earth right here, it's about 10 to the minus 10. It's very small. You live in an extremely small gravitational field, even though you may have to have knee operations, okay? But on the other hand, what you'll hear about from Barry and Kip is places where this number is closer to 1. It's huge. And those are places where around black holes and other places, the beginning of the universe, and so forth. And the other quantity is v squared over c squared. This sort of a measure of how much motion there is. And that's velocity divided the velocity of the objects divided by the velocity of light squared. So that quantity allows you to estimate h. So here, for example, for the two trains coming together, and by the way, trains in the United States don't go much faster than this nowadays. That has not been much advance in that. Maybe in Europe, but not here. Not in the United States. So let's pick 10 to the 5 kilograms for the mass, the velocity about 100 kilometers per hour, a collision time of a third of a second or so. Yeah, and you have to be far enough away so you're not looking at Newtonian, just a new induced field. You have to go far away enough so that you're looking at the radiation field, the field that carries these waves. So you have to go out a wavelength about, and that's 300 kilometers. And the h value you get is 10 to the minus 42. And that is truly impossible. We can't even do that now. And that's why Einstein probably made that statement. So he might have very well looked at something else. I mean, he knew about stars, and he knew about binary stars. And these people, he did not know about the galaxy. The galaxy was something that was being discovered at the time. And so, but suppose he put numbers into that. And he takes stars that are going around each other once a day. Here are the two stars. And suppose they're at a distance of about 10,000 light years away. He might have guessed at that. It might have been 30. He probably didn't know exact number for the size of the galaxy because he really didn't know about it. And you get an h value, which isn't pretty small. It's 10 to the minus 23 with a period of half a day. Every half a day, half a period. Every half day, you go through a thing that looks the same. So you look for gravitational waves with a period of half a day with a strength of 10 to minus 23. That's what we would do now. But in his day, he would have said, well, how much energy is being taken away by gravitational waves? I'm not going to describe that formula, but if you look at it, that's what that gives. And you would get something like the following. I'll just say what the end result is here. You would have gotten that it would take 10 to the 13 years, 10 to the 13 years, for those stars in a telescope to look like they were changing their distance, their separation. It's clearly hopeless. And so, in both ways, as an astronomical thing and as a technical thing, I can completely understand Einstein. Now, it turns out in our epoch, finally, there was a situation where that experiment that I just described to you, or the measurement I just described to you, was actually done. But was done fairly trickily. And this is sort of 100 years later, the technology has changed, and what we know about astronomy has changed. And this all becomes possible. And the thing is, these are Nobel Prize winners, these two. This is Russell Hulse, who was a graduate student at the time, and Joe Taylor, and they both were at the University of Massachusetts at the time. They went to Princeton because this was a major discovery, and they got scooped up by all these wonderful places. And what they discovered was a system of, they didn't know it, but they discovered a pulsar. They were looking with a radio telescope. They looked, and they used the Arecibo telescope, in fact, the one that got into trouble in the big hurricane. And they listened, and they heard a thing going brrr like that. And it was going at about 17 times a second. That's a pulsar. And these are neutron stars, stars made completely of neutrons. And they have the mass of the sun, and they're about the size of Stockholm. It's really unbelievably dense thing. And what they heard is the pulses coming from that, but they weren't going at a regular rate. Sometimes they were going a little faster, sometimes they were going a little slower. And it turns out when they mapped this, they kept looking at it, they found that for about 4 hours, and this is the model of it, it turns out to be a pair of neutron stars, and they're going around each other, and when this pulsar, which is sending its pulses to the radio telescope, is moving toward the Earth, which is over here, it goes a little faster, like from the Doppler effect, and when it's moving away from the Earth, it goes a little slower, and that's what they saw. And they mapped that, and they watched it for many, many years. This is time over here. And they saw it in 1973, and they kept watching it. And what they noticed is all the wonderful tests of general relativity were done by that system. But the one that was most telling and most interesting for us today is this one. It's the one where they plot the length of time it takes for the orbit to complete. Every time you go around once, it's the period of the orbit. And it's being plotted here. This is in time, epoch of watching the system. And this is the period of the orbit getting shorter and shorter and shorter. These are minus signs over here. And the dots that are in here are their measurements. And the line that goes through them is the prediction from the 1918 paper with a factor of 2 correction that Einstein made of how that system should lose energy due to gravitational waves. So that was the very first indirect measurement, but the first measurement of gravitational waves. A really profound thing, and it won the Nobel Prize. Okay, so then the next thing that happened, and this is again, it happened because of technology changes. And what happened, people began to have the fact that you could think of these very small strains, and you now had equipment, as the technology changed, where you could think of making a measurement. And the first person who actually thought of that was Joe Weber. He's right here. He was a professor at the University of Maryland. That's him. And there he is with his invention. The invention was, by the way, also an invention made together with John Wheeler, who was Chip's thesis supervisor. Okay? And what it is a great big bar. It's like you can see how big it is. It's as big as the man, maybe bigger. And what Joe was hoping will happen is that a gravitational wave will go through this thing, stretch it momentarily, and leave it singing, much like you hit it with a hammer. And there he is attaching little strain gauges to the device so he can hear that with the electronic equipment that was becoming available. And what happened is, to his misfortune, he saw something. And in fact, he saw something. He made several of these and put them in different places in the United States. He invented the idea of using coincidence methods to do this. And he had a system like this in Chicago, the middle of the United States, one in Maryland, another 8 miles away from his office in a golf course in Maryland also. And he saw coincident pulses. And in 1969, he published a paper which said he had discovered gravitational waves. And it turns out that many, many other people became interested in doing that. In science, that's what always happens. A stunning result like this can be tested by everybody else. And to his misfortune, nobody else saw these waves. Nobody else saw these pulses. And now we know why people didn't see the pulses. The strength, we'll talk, and this is something useful to remember, the strength that you need. And he was able to measure with these things a strain of about 10 to the minus 15, 6 orders of magnitude, bigger than what ultimately you needed. Okay, I'm sorry, okay. I didn't realize that was happening. So, what happened is people began to think of other methods of doing this. And one method of doing it, I'll describe here, is not with a bar, but rather with a thing which really, in the end, was more successful in making the real measurements. And that is to look at free masses, like that picture of the gravitational wave. A mass over here, and you put another mass over there, a goodly distance away, and you take and measure the time it takes. You want to measure their separation as changing as the gravitational wave comes by. That same picture of all those dots that I showed you. And so the idea is really simple. You take and have a light, send it, put a clock on those, put clocks on the masses, or actually, let's start that way. Clock here, clock there on those masses. Send light, measure the moment when the light left this mass, and find out with another clock over here the time when it hits that mass. That's a way of measuring the distance between those two masses. And then let the thing unfold, and as the gravitational wave comes along, it'll change that time because it's changing that distance. It's as simple as that. Now, if here's the idea, and this is a way which actually almost works. Here you have a laser and a beam splitter, which is a device that splits the light. And that's in the picture I showed you, that would be the red square that I showed you. Here is a distant mass, and that's a mirror. And there's another distant mass. And remember, the gravitational wave is coming down. And what it'll do is it'll stretch one of these and compress this, and it'll flip. Then this one will stretch, and that one will compress. And here is the way you make that measurement, which is effectively timing light. So what I'll describe as it goes along, where it's red is light. And we're thinking of red lasers when they made this picture. But what you see is the waves. These are the actual waves inside the power of the light. And where it's red is where there's light. If you do it right and make the time here equal to the time of light there, you get no light going to the photodetector. That's the idea. And so we'll show that's for the photodetector. Now, when you move these masses, one out, the other one in, you'll see that there is light when the motion makes it so the path lengths are no longer equal. And that is, in fact, the basis for the entire experiment. It's no more complicated than that. The big problem comes, you have to do it extremely well. And here is how well. Kip comes on the scene. I met Kip in 1975 when he and I met in Washington, D.C. He was thinking at that time, he was giving testimony to a committee, and he and I spent the night talking about what kind of experiments are interesting to do. And he was at that time, had already the most successful group, I think, in the country doing theoretical gravitation. And he was hoping to start a group, or have Caltech start a group in experimental work. And what we came on is that Kip, at that meeting, he and I talked about that ultimately this technique that we were just talking about here would be a good thing for Caltech to work on. But he told us something then already, that you couldn't just do it in this haphazard way, that it had to be done. And he was one of the first to tell us that if you want to get into business, you had to measure H's, or these strains, delta changes in length, divided by the length of 10 to the minus 21. I think this is Kip about that time. He'll tell us if I'm wrong. Yeah, he's agreeing. Okay. And what the big thing is that if you make something, and now we're getting on mixing times, but that's too bad. Suppose if you go to something as long as 4 kilometers, and you do the little bit of arithmetic that's associated with that, you find out that you have to measure distances at the ends, that motion, of 10 to the minus 18 meters. That's something like 1,000th the size of a nucleus of an atom. That's very hard. And here is the challenge that this threw at us. If you want to use light to make that measurement, light has a wavelength of about 10 to the minus 6 meters. You have to go 1,000,000 times a million times a million, more sensitive to the wavelength of light to get into business. That's what he was telling us. If you want to use light to do this. But then you had another problem, which in the end turned out to be much harder than that problem. And that is, even though you might have made a wonderful method of measuring things, their position with light, the things that you're looking at are not going to be standing still well. They're going to be kicked around by everything in the world, especially the world. And because you and I are sitting right here where we're being jiggled around by the ground by about 1 micron, at least a few microns. So 10 to the minus 6. So you got another factor of 1,000,000 times a million. And that one was a really hard one. And so here is the things that went on, and now the rest of this is really about people. Because people are critical to getting that factor of 1 billion and 1 billion. Billion, let's say, well, a European billion. 10 to the 6 times 10 to the 6. So, a guy who really helped a lot in this thing was a guy named, who was not so heralded, is a man named Pirani, who was a theorist, who told us, yes, it was possible to measure gravitational waves with things freely floating around. That was a big, big challenge. There was a lot of worry about whether you could ever extract any kind of measurable signal from gravitational waves. And he showed us that there was an invariant way, didn't depend on the coordinates that you used, of showing that a gravitational wave was moving the masses, changing the space. And that's, of course, exploited in this. And several ideas, and these are all people who were critical to it. Some of the gimmicks, some of the tricks that you need, and some of the tricks were first exploited in a small prototype at MIT, but it was not a very good prototype. But the idea is, I won't describe that picture anymore to say the following thing. We knew already that you had to use lasers. You couldn't use just a very weak light source. The other thing you needed to is you somehow had to make the light go more than once back and forth. You had to bounce the light back and forth. And you had to do tricks to get around the noise. And there were tricks you had to modulate the light. You had to use all the cunning tricks. And the other thing you had to do is you couldn't put the masses right on the ground. You had to somehow float them so the ground motion would not make a signal so large that you couldn't see the gravitational waves. And all those tricks were tried in this prototype. But the people who really did it right and who actually demonstrated to all of us that this was possible was the group that's up on top here. And you'll notice that this is the group that was in Garching and Max Planck group. And here is Heinz Billings. He was a guy who worked on bars with Weber, was severely disappointed. The whole group, after they did it, they showed they were one of the first and most accurate to show that Weber's experiments were not right. And so they were fishing around what would be the next thing to do. And instead of quitting, they decided they were going to go into this interferometric method of doing this. And here they are, and each one of them, the one who's in the room here is Albrecht Rüdiger. He's somewhere in this room. I haven't seen him. But unfortunately, most of them are dead. Walter Winkler is still alive. But Frau Schnupp, and we have celebrated her. Her name is now ingrained in the apparatuses we have for a particular trick of making it so you can see the fringes better. Maischberger was deeply involved in hanging all the masses, not just the mirrors, hanging everything. We didn't think of that. Just hang everything. You have to hell with it. You just learn how to do interferometry with things that are on suspensions. Forget about it, how difficult it is. And the same thing with Rüdiger. He was also advocating that. And here's Roland Schilling, who invented all sorts of ideas of how to get toward that factor of 10 to the 12 in sensitivity. He also invented, along with Ron Drever, who we'll talk about in a minute, the idea of power recycling. So then there was another group. So they were, what did they do? We'll talk about a little more, but they built a 3-meter prototype, much faster than the people at MIT did. And they showed that a lot of the ideas were right. They also showed that a lot of the thinking that had been done ahead of that had mistakes in it, that we hadn't thought it through properly, which was very important, especially the scattering, light scattering. That's something they discovered. Well, here's the other group that was very important in this development. This is the group at Glasgow. And here's Ron Drever. Ron Drever later came to Caltech. and worked there, and we'll talk a little about that in a minute. But Jim Huff was his student, and here's Brian Mears invented a very critical idea that has now become important in these interferometers. We'll get to that in a minute, but to add another mirror in a very unlikely place. And Harry Ward developed the ideas of how one might align systems like this. And that group was all at the beginning. They invented a whole bunch of new ideas also. And that group was critical in this business of going to the 10 to the 12 in the position sensitivity. And the things that actually then followed this were instruments. More prototypes were built. Caltech, when Ron Drever went to Caltech and Stan Whitcomb was hired, what happened, they built this instrument. I wish I had more pictures of it and more of the pictures of people, but they built this 40-meter instrument. And that's still operating. That 40-meter instrument was a test bed for the things that went into the LIGO, into the actual LIGO. And here is the other experiment that was done by the German group. And the German group with David Shoemaker, who was had an import from the United States at the time. And they built a 30, after they got done with their 3-meter prototype, they built a 30-meter prototype and showed that the scaling laws worked. That was absolutely critical. And they then, in fact, make a lovely statement in here. At the end, you can't read this, but I'll tell you, they got to past the sensitivity of the bars. The best bars. They did better with this instrument than you could do with Weber bars. And that was an extremely important statement because that made everybody say, aha, this is the wave of the future. And if you're now going to build something big, you're going to have to do it with this something that's going to detect this kind of thing. Here's the group at MIT a little later. The reason why I like this is because it has some of the people who are now leaders of this thing, and they were young people. There's Nergis Mavavala, and then there's Peter Fitchell right there, and in the back is Brian Lance, and this is Mike Zucker, who was at Caltech working on the 40-meter. He came to MIT. This was, after a while, it turned out those two groups became sort of completely interchangeable, and that was a lot of things were done there. I won't go into all of them. All preparatory to what I'm about to show you. So this is out of time, Sirens. It should really belong in Barry's talk, but I have to show it because he wants to show other things too. This is actually the interferometer that actually made the detection. And I'm not going to walk you through except to show you where some of the things you already know exist. Here's the laser again. There's the beam splitter. Here's that distant mirror, and there's that distant mirror. Here's the gravitational wave coming down. The things that have been added to it are these two masses, this one and that one, that make it so that this becomes something called a Fabry-Perot cavity. It's a way, effectively, of bouncing the light back and forth about 300 times. And in here, about 300 times. And then here is the photodetector. And again, you operate it in such a manner that no light goes to the photodetector when there's no gravitational wave. And then here's the idea that both Ron Drever and Schilling had. You put another mirror, which you haven't seen before, between the laser and the beam splitter. And what that mirror does, I will just describe what it does, and I'll show you, is it takes the light that isn't going to the photodetector, that comes out of the laser, goes into the interferometer, is not going to the photodetector. It would normally go back to the laser, but you make it so you bounce it back into the interferometer and build up the light inside the interferometer for that reason. And that makes it as though you had a very much more powerful laser. A very clever idea. Then here's Brian Mears' idea, and that is that you put another mirror, which is not, this is not immediately something that everybody can capture because you need to know a lot more than I told you why this works so well. But what does it do? By putting a mirror between the detector and the beam splitter, it makes it so you can tailor the response of the interferometer. You can make it have different shapes, make it have so that it's more sensitive at certain frequencies and stuff like that. And this is called a power recycling mirror, and that's called a signal recycling mirror. And that's an important part of advanced LIGO. So this is the advanced LIGO detector. Okay. Now, that's the technology of the how do you make the light get that factor of 10 to the 12. We're not quite done with the technology of how you make the ground motion small enough. But first, let's talk about how you begin to build up the idea that you don't want to do just prototypes. You would like to actually build a detector. And that happened in about 1980. that we began to think hard about how expensive, how might you build a system that actually could detect something. And we were driven to that for many, many reasons. It was hard for students, at least at MIT, to keep working on something which didn't have a physics result, had only an engineering result. And I don't know, at Caltech it was different. They had a different attitude about this. But the thing is that what we began to think about is really, we asked the NSF if we could do, and we were also encouraged by the NSF, and we'll get to that at the very end, to make an industrial study with industry to find out where could you place a thing that was big enough, and we thought of 5-kilometer arms, maybe even 10-kilometer arms, and could you get the lasers, and how would you make the vacuum system, and all the stuff that goes on, that if you want to convert a thing on a tabletop into something very big. And there was a study done, and there are two people here who were quite central to this. Peter Salson, who helped in that. He was a postdoc who had come from Princeton, and Stan Whitcomb, who had been brought on by Caltech, and he wanted to be part of this same study, and this is called the Blue Book study. And it did that. A little bit later, and with very significant differences, because during that time, between 1983 and 1989, we did a bad thing. We had Ron Drever and Ray Weiss trying to run a big project with the help of Kip Thorne. That was hopeless. And it was noticed by a committee that met in 1986 that had been asked to look at this whole field. And that committee had been started by Richard Garwin, a very significant personage in American science, who said, look, if you're going to persist with this, you better have a summer study. And that summer study said, look, it's a wonderful experiment. Don't hold back. Build 2 of them. Make them the long length. They said everything right. And they said, you can't do it with that crazy bunch who are running it. Okay? And said, get yourself a director. So we got a director. And that director was Robbie Vogt. And Robbie Vogt guided us through writing a proposal which was really a textbook. It's a beautiful proposal. It cost us a lot of time. It's a first real document that showed a lot of the techniques and how it might build this and costed it properly. And what happened is that proposal became a joint proposal of Caltech and MIT. And there's one very elegant thing that Robbie Vogt did, among others. He did something which was he coupled, in the process of thinking about this project, he coupled an engineer, if we had an engineer, and we didn't have enough of them. And Barry later, when he took this over, realized that. But we had some engineers. But we had a lot of scientists. And the idea was, couple an engineer who knew how to count money, but also knew what was practical, with a mad scientist who wanted to make sure you didn't compromise the experiment, and couple them together so that they designed something and estimated something which was going to be both realistic as well as able to do the experiment. And that was a very good experience. I can show you only some of the people here who did this. And so well, you recognize some. There's Ron, there's Kip, and then there's a chief engineer at the time, Bill Althaus. Here's an engineer who stayed with the project. I couldn't get a picture of the vacuum engineer at the time who was doing this, and that is Bowd Moore. And here's Larry Jones, and Larry Jones was tagged with me, and we helped design the big beam tubes and so forth. And so this was a very important moment in the history of LIGO. Let me go quickly more back to the science a little bit, or the technology. And that is, this is the kind of thing that evolved when in that proposal, we want to show people what limited the performance of a gravitational wave detector. This is, in fact, a plot of the things that limited the first detector. Barry will show you the evolution of that detector. But I just want to walk you through some of the things in here which are still important. What this is frequency. In other words, this 1 hertz, 100 hertz, that's an important region. 10 kilohertz over here. Here is a strain of about 10 to the minus 23 per bandwidth. I'm sorry, this is you're using spectra. So if you want to go back to what I was telling you, you have to multiply this number by the square root of the frequency. That's a detail for those of you who want to follow. But that's not important. What I want to show you is what was limiting this detector. At high frequencies, it's this line, and that's the amount of light power you had. At low frequencies, it was limited by something else, but I want to continue this because this is important for Kip's talk. This is part of what's called the quantum limit. The amount of light you use to tell the position of the mass is If you use more light here, having more photons, you can bring that down. But you pay a price for that. Over here is another piece of that same noise, which is called the radiation pressure. And that is, if you use more light, you push on the masses, and there's noise in that light that pushes the masses around. And many of you who have led quantum mechanics know that there's something called the Heisenberg Microscope. This is just the Heisenberg Microscope macroscopic. Okay? When you try to measure better the position of something, you impart more noise momentum to it. And that's what this curve says. And this is something we're now battling. And you'll hear more about that from Kip and from Barry. The other noises in this thing are, for example, how well can you get rid of the ground noise? And at the time when we were designing this, this limit is the noise that shakes the ground, the seismic noise, and that makes a limit at low frequencies. And then there's here, this limit is the fact that everything is room temperature. And when everything is at room temperature, every surface is shaking due to phonons, so the sound waves. In the sound waves that are generated by just the fact that there's energy in the heat. So that's thermal noise. And here are some things that still plague us. Here is the thing that made it cost so much money. If you had a vacuum that was only as good as a certain value, this is a value that you could get moderately easily, that would be a limit for a detector that would be better than this. And I have failed to tell you something. That proposal in 1989 proposed a two-stage procedure. It's proposed we build one that we know how to build now, or almost know how to build now, and another one we hope to build in the future. And that would need much better vacuum than this, in fact, down here. And that, getting that whole assembly together, making the vacuum good enough, was an expensive proposition, but we succeeded with that in a very unique and interesting way. And so what remains as a noise is this one right here. This is very important noise. And that's the last thing I'll show you in this picture. You'll notice it gets worse and worse and worse the lower the frequency. And that is a noise which we have to contend with. And it's the noise that we will have to continue to contend with. There are two noises in this we have to continue to contend with. This is one of them, and the other one is the one I already told you about, which is the quantum noise. But this one is something which is not easily thought about always by people. You have the ground shaking, and that's fine. But when the ground shakes, there's another piece associated with that. A wave traveling in the ground causes the density of the ground to change. And let's say this bunch of flowers is the mirror. And here are these waves coming by. And as it moves, here's this compression going on in the ground like that. And as the compression goes by this, it's a little higher density over here. That pulls the flowers over to the ground. That's a force on the mirror. That's plain Newtonian gravity. And that's the noise. The waves are there, the acceleration there, but the density changes in the ground make a change in the force on the mirror. And we have to contend with that. And also the density changes in the atmosphere. And there's the Hungarian group that has joined LIGO has thought about methods of measuring the barometric pressure carefully enough so that you can measure that. So those are noises that are still with us. And we have to learn how to get around them. And that's one of the reasons why people propose the LISA experiment, which Kip will talk, well, I think, yeah, Kip will talk about. So, all right, that's sort of a little quick guide through all the things that contaminate the gravitational wave signal. The last thing I want to quickly say, and this is really in Barry's part of this presentation, is what we did to make the final steps in getting rid of the ground noise. Not the gravity gradient noise, but just the acceleration. And this was a contribution to LIGO, for advanced LIGO, done by the group in Scotland. And this is a very elegant suspension. Here's a spring that's attached to the ground, and there's a mass. And this is a suspension. And if you wiggle the suspension quickly, the thing you hang it from doesn't move. So you do that once, then you do it once again, you do it once again, you do it 4 times. And here's that very precious mirror that's going to be reflecting the light. And that 4-stage suspension is a critical part of LIGO, and especially a critical part that we made a detection. But even more important, as far as I'm concerned, is this thing, which is much too complicated to tell you about, but I'll tell you what it does. It's an active system that gets rid of the ground noise. And you have a lot of experience with that in your hearing. I don't know how many of you use these noise-canceling headphones. I'm sure that people here, yeah, okay. It's the same principle. What you do is you put a very sensitive seismometer on a platform and measure the motion of the platform. And then what you do is you push on that platform to get rid of the signal in the seismometer. That's the same thing you do with the headphones. That the headphones listen to the sounds that are coming in. They generate a sound that's the opposite sign in the headphones, and you don't hear the outside world. You only hear the music that's on the other part of the headphone. That's how that works. It's the same idea. It's an active system, and that is absolutely critical to us. And that was developed both by Ligo and Stanford University. Okay, now people again. I want to give a special credit to Richard Isaacson, who is in the audience, and I know he's going to be shirking when his name is mentioned, but I want to tell you what he did for us. First of all, he was a first-class scientist in this business to begin with. And he wrote a paper quite early in the 60s where he showed a thing that was very controversial at the time, that gravitational waves actually carried energy away from a source. That was heavily debated. A lot of people thought it was just a coordinate problem, but he showed there was actually energy leaving a gravitational wave source. And here he is. And what he did, he became the discipline chief for gravity at the NSF. And he convinced his boss, Marcel Barden, that this crazy idea that we all had really had merit. And he did it at a time when it was not so easy to do that. We didn't have the technology in hand, and we didn't know what sources we were going to see. And he had to sell this idea to his boss. And he did a magnificent job of it. Then he sold the whole agency on this. Okay? And that's something which is spectacular. Without him, this would not have worked. And these are some of the people who were influenced by that. And I want to say something special about these are directors of the NSF, which were critical to our development. Rich Isaacson was actually deeply mixed up with Eric Bloch, with his boss, and Eric Bloch was an engineer. And the same thing happened at MIT. The engineers were the first to recognize at MIT that this might have some value. The electrical engineers around me. It wasn't so much the physicists. And so he had the idea that this was exactly the right thing for the NSF to get into. Something very risky, but had a tremendous payoff. And so Eric Bloch pushed it. And then when things really began to happen, and there were people who didn't like the idea that LIGO was beginning to use money from the NSF, there were people in the astronomy community that actually resisted it. You can read the newspapers as well as I. And Walter Massey, who was head at that time, a little later, actually told these people who were very influential, no, we're going to do this because it's the right thing for the country, and it's the right thing for the NSF. And it was quite a struggle, and he was a magnificent person for doing that. And then, to make it all happen, the head of the NSF at that time, and this is in Barry's epic, was Neil Lane. And Neil Lane helped the NSF figure out how to go to Congress and say, look, the NSF needs a line item for big projects. It hadn't done big projects before, but that's what we need to do. And so there was something new invented, and that's how you get money. You don't go to Congress complaining. You never go to Congress complaining, stop this and give it to us. That's the wrong way to do it. What you do is, here is a good idea. Why don't you try to fund this? And the idea was, the NSF has all this science. We sometimes need to build big projects, and we need big chunks of money periodically. And that's still in the NSF budget line. And Neil Lane was absolutely critical in doing that. And now last slide is, this is when the project, as far as I'm concerned, actually got started. Because then enough people were brought in. Finally we had somebody who understood that it took more than a skunk works to make things happen. Barry came. We were lucky that Barry came, partly because an unluck of the high energy physicists, the superconducting super collider got killed by, I think it was Clinton that killed it. And he brought Gary Sanders, who was in the audience, who was a project manager, who was a superb project manager. He then hired more people. Thank God. He hired Albert Lazzarini, who's also in the audience, and Dennis Coyne as a chief engineer. And he has been with the project for a long, long time. He's now doing something very interesting, different in this. And what was happened is that Stan Whitcomb was brought back from industry. It was already under Robbie, but he really was made and became sort of the chief scientist of LIGO. And I'm done. Thank you very much.
Okay, thank you very much. Yeah, you will have your chance to come up later also. Thank you. Okay, so Professor Weiss was the one who really laid the foundations for much of the design of this gravitational wave detector. And the next speaker then, Professor Barish, he was the scientific leader who managed to scale up the Ligo project in a stepwise fashion, reaching the advanced Ligo, which was really the facility that managed to detect the gravitational waves. So please, Professor Barish.
So I guess everybody knew before they were here today that this is a very long story. And we're now to the beginning of the next part of the long story. I'm going to try hard to stay on time. There's 21 years more to go after the story that you just heard, which took a long time. So I'm going to pick up the story in 1994. And in 1994 was when we received, for the first time, project funding to actually build something, which is the Ligo detector, with all the responsibility of getting tens of millions of dollars a year for 20 years, and defending it during a period where we saw nothing during that whole time. So the first thing that people should realize is that the National Science Foundation not only took the risks that Ray mentioned in taking on this project, doing the R&D and so forth, but after it was taken on, they had to defend a project with all the risks that it had for 20 years with essentially no results. We basically set various limits because we didn't see anything, but for no results. And so we're probably indebted more to the NSF than one can imagine in taking on such a project. We organized it by a collaboration between Caltech and MIT, and that shouldn't be lost in the story because we now have 1,000 scientists around the world, but we have at the center of all this what we call the Ligo Laboratory, and the Ligo Laboratory is the group that actually has built and made the detector work. The responsibility for the detector is Caltech and MIT's, and we've organized that as a project. We have about 150 technicians, scientists, and so forth. The scientists in this group do their science in what we call the LIGO Science Collaboration, but the instrument has been built by us. The present director is Dave Reitze, whose picture is up there. And the deputy director is Albert Lazzarini, and they're running it today while we're doing all this fantastic science. And earlier, after I was director, was Jay Marks, who led it during the crucial period when we took on advanced LIGO. Next, in about 1997, we realized that the Caltech and MIT collaboration didn't bring all the elements we were going to need to succeed at this project, and certainly not all the scientific ones. So we created what people have heard about today, and that is the LIGO Scientific Collaboration, bringing in talents varying from experts in lasers to experts on, and now, artificial intelligence, in order to take the whole breadth of talents that can be brought to this incredibly difficult problem and pull it together. That's grown from what started as tens of people in a collaboration run by Ray, who I appointed at the time to run the collaboration, to a collaboration now that's very democratic with elected officers and is run presently by David Shoemaker, by Gabriela Gonzalez during the period where we made the first detection. Before that, by Dave Reitze, who now is running the laboratory, and Peter Salson, who you heard about, was after Ray. This is a magnificent success of international collaboration, of the ability to bring in the talents that we need, whether it's technical, whether it's data analysis, whether it's theoretical, together, working together side by side. We have 18 countries involved in LIGO, more than 100 institutions, and about 1,200 collaborators, of which 1,000 were with us long enough that they were credited with authorship on our discovery paper. The interferometers themselves are organized with some critical people that have run it. From the beginning, we've had somebody who's at these sites that are distant and not close to a city and run by two people, originally Fred Robb and Mark Coles, who later went to the National Science Foundation, and presently by Mike Landry, who newly took over the Hanford Observatory, and Joe Giammi in Livingston. So if you visit either of those laboratories, that's who you see. And they're remote, one in distant Louisiana, far from any city, and the other on a DOE reservation in eastern Washington. Just to show you what things look like in the real hardware, this is a picture of LIGO if you walked into the big hall, where this is the vertex that Ray showed, where the light then goes out in two directions. This big thing here are called gate valves. They allow us to preserve the fantastic vacuum that Ray talked about that we need to while we work and evolve the instrument. These instruments that you look at here aren't quite as simple as what Ray showed, and part of that is building in enough flexibility, all these ports and all the ways of getting in, so that from the beginning we understood that if we're ever going to detect gravitational waves, what we built at the beginning wasn't going to probably make it. So we had to be able to evolve the instrument, and in ways that we weren't sure how to do it. So we, as much as possible, we asked the NSF for more funding at the beginning and made as flexible an instrument as we possibly could. We built it. By the end of maybe 1999, we had it built, and then we started making it work. And this picture kind of illustrates how we approach the next 15 years. This is the same curve that was shown by Ray, where it's limited on the left side by the shaking of the Earth, on this side by the amount of light, and in between by the noise on these test masses that we talk about. And better sensitivity is the bottom of the plot. It's the same scale that Ray showed. And this is the frequency band that's available to us to look for gravitational waves. It's the audio band where the Earth is the quietest. Each curve here is basically subsequently a different time. So our strategy basically was to turn this on. It was at whatever sensitivity it was. This isn't very sensitive. Lick our wounds, look at what we did wrong, what was limiting it, take time off, run it again, and it evolved to a better curve, a better curve, a better curve. This is about the first 5 years of the detector. We kept doing this for 10 years. At each time, we would search for gravitational waves. Each time, we wouldn't find gravitational waves. Each time, we would have a better limit, because this was better, on how well we knew they didn't appear. And so we wrote a series of papers, but they basically were null papers during that period. Along the way, we got to the point where we were as good as we had proposed, except maybe a little bit at the low frequencies. And that's this curve here. So this is the initial detector that we were funded for by the National Science Foundation on the same kind of graph, as good as we could. We knew very early, as Ray had indicated, that we wanted to do this in 2 stages, that we could incrementally improve things, but only so far without making some major changes. So we had done the detailed R&D necessary to develop the techniques and the apparatus itself, the detailed designs that would go into a second generation detector. And that was what we called advanced LIGO. Interestingly, we called it LIGO 2, but the NSF, in their wisdom, decided that we were sneakily talking about LIGO 1, 2, 3, 4, so they asked us to change the name, and it became advanced LIGO. With advanced LIGO, we then built it between 2010 and 2013 or so, and started turning it on. We basically had learned a lot, so we turned it on a lot faster than we had the initial LIGO, getting near design sensitivity. By 2015, it started to work well enough so that it was better than what we had built for initial LIGO, and that is shown here. The key people, by the way, for advanced LIGO, some of the key people I show over here. Dennis Coyne, who was shown earlier, has stayed with us as our chief engineer and was the engineer responsible for the fantastic engineering that goes into advanced LIGO. David Shoemaker, who's running the collaboration now, was basically the main scientist responsible for advanced LIGO. And Peter Fritschel for the incredible optics that we use and the way the interferometer works itself, and two people, one in each laboratory, who have been the most responsible for the making this thing actually work in the field. And so we started to make it work, and the two detectors are in the two different colors here, and what they indicate is that despite the fact that they're physically in very different locations, they basically, in design, and as long as we do the same thing at the same time, they work essentially identically to each other. At this point, this had improved about a factor of 3 beyond where we were in initial LIGO. Our goal was to improve things a factor of 10. This is improving the sensitivity a factor of 3. And what to realize is that the sensitivity tells you how far out you look in the universe. So if we increase the sensitivity a factor of 3, we actually improve how much of the universe we're looking at by the cube of that, because that's the volume that's scanned. So an improvement of a factor of 3 basically gave us the ability to do what we had done in initial LIGO or more in 1 year, what we could have done in 27 years with initial LIGO. So we decided not to go all the way to here, but have a similar strategy to what we had in initial LIGO and use this as the first search. Because we had improved the concept for how we treat low frequencies, which was described by Ray, the improvement at, say, 40 hertz was actually a factor of 100, shown here. A factor of 100 is cubed in terms of the sensitivity we get, so we were really 1,000,000 times better than we were in initial LIGO. And that answers a question that's often asked to us: how could we turn this thing on, and after a few days, which is what happened, make a discovery when we had run it for 10 years before that, or almost 10 years? And it's really this factor of 1,000,000. So we turned on advanced LIGO and made that improvement. Again, this is just a picture to emphasize that the big improvement that made this detection, maybe the take-home message, if you want to tell anybody why and how we made the detection, was the improvement in this nice quadruple and fancy suspension system developed at Glasgow, and the isolation from the Earth by seismic isolation from the Earth by a set of essentially shock absorbers and these active seismic feedback systems that Ray mentioned, that, by the way, the reason they're so hard, it has to be done directionally, differently than the earphones in the airplane. We have to know where the Earth is shaking us, what direction, and correct for it. And that makes the system quite a bit more difficult. We turned on, and a few days later, this is what we found. So this was September 14th, 2015. 21 years after we received project funding in 1994. Not what my fantasies were, most of us, for what we'd first see. I would have expected, if I thought about what we would see, that we'd start to see hints of gravitational waves where our detector wasn't quite sensitive enough yet to make it definitively, and then we keep working in the future at making it more sensitive. We were lucky instead. We, of course, made big improvements, but we immediately saw a signal that stood out and looked very much like you'd draw to show somebody what we were doing. This is two different traces. One of them at the laboratory in Eastern Washington, Hanford Laboratory, and one in Louisiana, and they should look essentially alike. You'll notice the left-hand side is strain, the word that Ray used, and the scale is the scale he also showed, 10 to the minus 21. So the scale that we were detecting and got to the sensitivity to detect, and also the scale that had more or less been predicted by the range of sources that we talk about, was 10 to the minus 21, and that turned out to be, after all these years, right. And these are the two traces. If I take the two traces and plot them on top of each other and slide one slightly from the other one by 6.9 milliseconds, then they sat essentially right on top of each other, as you can see here. And the difference between the time between the two, I'll point out in a minute, gives us information that's crucial, especially for the future. So those are the two detections. By the way, we made a decision in 1994. Finally, we had to make the decision in 1994 how to orient these two detectors relative to each other. They can't be exactly the same because the Earth curves by 16 degrees between Livingston, Louisiana, and Hanford, Washington. But there was a rather large debate whether we take the two L-shaped detectors and make them parallel to each other or rotate them by 45 degrees. The reason you would rotate them by 45 degrees is it gives you the ability to extract more physics. That is, there's a polarization in these gravitational waves, just like for electromagnetic waves. So the argument to rotate them is exactly that. The argument to put them in parallel is what I showed you here, that we could put one on top of the other. We did it one on top of the other in conservatism, and of course, it's what made one event so convincing that we could put one on top of the other. But we couldn't tell the polarization information. That has come, and I'll talk in a minute, by adding a third detector that is oriented separately from us. That's the Virgo detector, and that has started to give us information on the polarization. We detected this event in September of 2015. Did we immediately know it was gravitational waves? Not really. Most of us, or some of us at least, had deep worries how we might be mistaken, how we might be fooling ourselves, or how we might be being fooled. Those two questions, basically in translation, were that we turned on a new apparatus, and in turning on a new apparatus, maybe it could generate some sort of shaky signals, but they weren't real. And in order to test that, you have to run it for some period of time. We calculated how long that had to be, and it was basically a month. In a month's time, we could look at all the bins of time in the two, correlate them together, and see what the probability is that you could get any sort of signal like this in the detector. And that's calculated to be a magic number in physics when you believe something, which we call 5 sigma, or the probability is less than 1 in some hundreds of thousands of years. So basically that was the first thing. The second problem was maybe somehow we were being fooled by some mischievous people or person who has superposed this on the data. And we just looked at the data and it really wasn't there. That, again, had to be studied in great detail by following. The idea was the following. The data comes together at Caltech, and from that time on goes around the world. In fact, this first event was seen first in Germany. It was the middle of the night in the States. And the data comes together. Once it's together, you could imagine somebody superposing an event on top of the data. To resolve that, we have to take it back to the laboratories where we had traced the signals and what they recorded along the way, and that required another study, which took about a month. So by middle of October, I think we had really confidence that we had made this discovery. We spent maybe another month seeing how well it fit general relativity, spent another month writing it up in great detail, writing it up in a way that we thought could be read by the world and not just by experts in the field, arguing about whether it should be called an observation or a discovery and things like that, with 1,000 people weighing in. And you can imagine somehow making that converge was a problem. We finally were ready to submit this to Physical Review Letters, our choice of where to publish this, by early December of 2015. We were about a week late because we were arguing too long on which adjectives to use in the paper. And at that point, Physical Review Letters, who had agreed that they would allow us to make the article longer than the standard article, and that they would review it specially, both very secretly and quickly, informed us that we were now too close to Christmas and they couldn't do it. So we held the article until January, and interestingly, our second event, which I show now, came on December 26th. So when we announced this event in February of 2016, we knew, but we didn't yet bring that to the public, that we also had a second event. So as convincing as the first event was, we all had a second event. It looked very different. You can see this has many, many oscillations. It's smaller, but we detect it as well because there's so many oscillations. That's a reflection of the fact that they're lighter, the two black holes that are colliding. It's also black hole collisions. This graph here just illustrates, it's the so-called Chirp Graph. This is basically time going this way, frequency going this way. It gets louder as the frequency goes up, and the so-called chirp that we describe as a signal. The second one, which is weaker, but in there longer, so we are able to pull out the signal, is down here. But if we look at basically the low frequencies that weren't available to us until we made the big improvement in the suspension and the isolation system, both of these signals were enabled by making those improvements at low frequencies. Of course, we've kept running. We finished that first data run with these two events in January of 2016. And at that point, we changed things, fixed things in the same spirit that I presented our activities through the period of initial LIGO. And we started a second data run, which maybe for most of us, we expected couldn't possibly be as exciting as what we saw in the first data run. That turned out to be wrong, as I'll show you. In the second data run, I show here we haven't analyzed all the data yet. We haven't made all our reports yet, but this is where we are today. We basically have reported 5 observations of probably black holes. One of them we don't call a black hole just because it's further away and doesn't give us quite the 5 sigma significance as a single event, but otherwise it appears to be like the others. So we have a set of events which start to let us look at distributions of the alignments of spins, the masses of them, and the difference in how long they are is the difference in how much their masses are, and so forth. So the 5th one here actually has a different significance. That's this one here. The dates are the 17th, the 8th month, the 14th day in 2017. So just this last August. So this last August, we detected an event that at the same time was detected for the first time also in the Virgo Detector in Italy. The Virgo Detector is very much like LIGO. I don't have time to show some interesting differences in how they approach the problem, but it basically has similar sensitivity once it's fully operational, will have similar sensitivity. This was begun by 2 scientists in parallel with the efforts that were described by Ray, Alain Breillet and Alberto Giazzotto. And in the present day, run a little bit like us, having a laboratory where the director is Federico Farini, and the spokesman, who I think is here today, is Jo van der Brand from Holland. And it's very near Pisa in Italy. It's not just the confidence, which of course matters, that somebody independent sees the same thing. That's great. And at this point, we don't really need that. We're pretty convinced that we're seeing gravitational waves. And we were in competition for 20 years, I think, to see who could see gravitational waves first. But it gives us new information, and that's shown here. With just the first detectors, we were able to locate, even on the first event, that it came from the southern hemisphere, and we knew to some number, 600 or 700 square degrees, where it came from. And the various events are shown here in how well we could tell where they came from before we turned on the Virgo detector. The Virgo detector, once it's on, because it gives us triangulation in where the signal they see compared to ours, where we take the time difference in the arrival time at the different detectors and the difference in the signal, because the antenna patterns are somewhat different, gave us this signal down here. And you can see that we now can locate, with the addition of Virgo, the location on the sky where a gravitational event came very accurately. This is something we've always wanted to do. And luckily for us, this happened just in time. And I'll show you that in a minute. First, let me reflect on what we found so far, seeing 5 events. We've seen where this is mass, and this is just the time passing, the number of events. These are each symbolically 2 black holes coming together, making a heavier black hole. They're all up here on the plot where this is mass. What was expected was black holes that would be down here. So we immediately, something we've always thought, using gravitational waves, would see different phenomena that are seen in electromagnetic radiation. And what we saw was large black holes. They're not expected. Just qualitatively, the reason is the progenitor, or the heavier object that makes these black holes, is supposed to be a heavy star that decays and makes a that dies and collapses and makes a heavy, makes a black hole. There aren't, we believe, very heavy enough stars to make these very easily. There has to be either a special place in the universe where it's low enough metallicity or doesn't have heavy elements around so it can live longer, or dense clusters or primordial production that made these black holes. And that's our next problem, like all these problems in physics, is where do these black holes come from? There are handles on it. We hope to get more information on the spins, on the orientations, on the distributions, and to be able to resolve that. The second thing that has come out of the very first events is tests of general relativity. This is a graph where we just put in a form that would be qualitatively different from general relativity, just to test it, not a particular theory. One limit of that is to look at the physical place where you would have connected to the transmission of gravitational waves what we call a graviton. Very much like for electromagnetic waves, we have a photon. Or for particle physics, there's all the particles. A graviton, if it existed, it does not exist in Einstein's theory, could have a mass. And what we're able to do is, if it had a mass, it changes the detailed shape of that trace that we looked at, and we're able to say already, just based on these very first observations, that if there is such a mass, it's less than 10 to the minus 23 electron volts over c squared. So those are tests. The next was a rather fortunate coincidence. We got Virgo into our system, working together 2 weeks before this happened. Later in August, by the way, we were scheduled to turn off at the end of August, so this happened, fortunately, just before we turned off. Well, for the first time, we saw a second kind of event. The merger of a binary neutron star system instead of a binary neutron star system instead of a black hole system. What is a neutron star? Again, Ray mentioned neutron stars. It comes from the collapse of a star also, we believe. But it's dense nuclear matter instead of a black hole. If it's dense nuclear matter, if we have 2 objects going around each other, it has all kinds of nuclear effects in addition to just the general relativistic merger. And this is nuclear physics in extreme conditions. And we can then see all kinds of effects, including the fact that the nuclear effects can give and emit light in various ways. we basically could tell from what we saw that these were much lighter, like neutron stars are supposed to be, than the black hole events. They were a distance much closer than that 50 megaparsecs instead of 20 times that we saw for the black holes. And fortunately for us, the signal was also seen 2 seconds later in an astronomical instrument. That was the Fermi satellite that monitors gamma ray bursts. This is a picture of our signal and put on their trace and where they saw a signal. Over here is the same pictures of the location on the sky. Our location on the sky is these long pictures here if it was just LIGO. But when we add Virgo, it's this little ellipse here. And this is the position as determined by the Fermi satellite. One thing that makes me feel great is that we're the ones that actually have the better location, even though we're beginners at this game. So, and that's very important for the future. So this picture is what we think is the indication of what the future is going to portend. This particular event, then having the confidence that it was seen both in an electromagnetic instrument, the Fermi Telescope, and us, could be studied for hours, days, and weeks after that, and has been. Looking at gravitational waves, of course, looking for it with neutrinos, looking with visible and infrared light, radio waves, gamma rays, and X-rays, and so forth. Using this, a whole set of collaborations and conclusions have been made from this one observation already, which, by the way, we announced only a little over a month ago. 2 weeks after the Nobel announcement, we announced the merger of two neutron stars. So even after whatever we got this prize for, we're still producing very interesting new things. I'll just give you a glimpse, I'm out of time, at a few of the different kinds of phenomenon that are and interpretation that came out of this single first coincidence event with electromagnetic instruments, kind of to wet your tongue at what's going to happen in the future. The first is an independent, pretty independent measurement of what's called the Hubble Constant. This is basically the rate at which the universe is expanding. It's done by in this case, optically identifying what galaxy it was in, and then otherwise from the information we have in the gravitational wave signal. And the answer, this so-called Hubble constant, is independent of and consistent with the answers that came in electromagnetic interactions. The second, which I won't go through in any detail, is that there's been a lot of phenomenology of what happens when objects like these neutron stars come together. We all know what a supernova is, the collapse of a star when it gets old and dies. This is tabbed a kilonova, the consequence of this coming together, and that's been studied now in all these different instruments and put together and compared with some of the phenomenology that's been developed for a kilonova, and at least the general idea confirmed. One consequence which is interesting is the possibility that we have actually figured out or seen what makes heavy elements in the sky, in heavy elements. A puzzle has always been, how on earth do we have very heavy elements? Where did they come from? You can go on a mine and find gold or platinum or other heavy elements. Where do they come from? We know most of the universe is made out of hydrogen and helium. We know how to make everything up to iron very easily. It's made in the same fusion process that makes the sun. The sun burns. But making heavier elements in nature, we don't really know. We do know how to make them in the lab. We make them all the time, and the periodic table has gone up quite high. We basically take a heavy element and bombard it with neutrons. Sounds familiar, neutron stars. So the neutrons are the way we do it in the laboratory. So the idea is very tempting that maybe in nature it's collisions like we just observed, that is neutron star collisions, that made heavy elements. This graph here is one phenomenological interpretation of that. And the yellow parts, which you'll notice are mostly yellow for gold and platinum, which you might have on your hand, come from merger of neutron stars, at least in this analysis. And so maybe all the gold and platinum that we sell on the Earth, we finally discovered comes from collisions like we've just announced, a rather interesting conclusion. Lastly, I just want to end with the future for a minute or two. We have now 3 detectors working. We'll soon have 2 more. We have one we're building in India, a Ligo, with the collaboration of the Indian physicists and Indian government. That'll be ready in the 2025 era. There's one in Japan that has some advanced techniques, which I'll mention, which should be working within the next few years, giving us better localization. This is an incremental plot of how well we think we'll be able to locate the position on the sky as we move into the 2020s. And you can see that with the addition of the other detectors, independent of where something comes from, we should be able to tell very well where it is and combine then with electromagnetic information. We have ideas and also plans for the future, and I want to end on that. First, as I showed you, we're still about a factor of 2 away from the design of advanced LIGO. That we will do over the next few years, again, in a matter of steps. And that gives us almost a factor of 10, 2 cubed in the rate or the significance of individual events. We have concepts for getting beyond that. We know that we should at least think and do the R&D and possibly ask to be funded for a concept that would exploit our sites where we have LIGO to their fullest extent. And so we've basically done conceptual designs of that. We can improve by making a much heavier test mass, by using a different material in the mirrors. We're presently looking at silicon, by lowering the temperature modestly, by improving a limitation we have, that is the coatings, the optical coatings on the mirrors that Ray showed, and by making yet a more powerful laser. If we do that, we can get down to the black curve that's shown in this plot here. And that will enable us to have more cosmological reach, which will be talked about by Kip, some of the ideas of what we might be able to do. Improve signal to noise, what we've learned is that we need to have events where we have such good signal to noise that we can determine things like the orientation of the spins of the black holes and so forth. And an event rate that's maybe 10 times advanced LIGO if we put in all these. This will require R&D, and we haven't yet the funding and haven't formally proposed to do it. The next steps are to do other reactions that we can do on the Earth's surface, but also, and this is some of those as possible, Kip will talk about those, but it's already basically in this community ideas that are fairly well developed for how you would move to the next generation detector. It's completely possible. We don't see any great technical hurdles in extrapolating this up to a detector that's a factor of 10 or so better than present detectors. What's the right detector is what we have to work on. And to do that, we have to set our priorities in science. We can't do everything. There's 2 main concepts right now on the table. One is to go underground, make the detector cryogenic so it's cooler. This very much helps the lower frequencies. We're going underground, there's less shaking of the Earth, cooling the detectors, you have less thermal noise. This is a concept that's been developed in Europe, and it's called the Einstein Telescope, and they've been working on it for about 5 or so years, and it's pretty firmly designed. Maybe not costed, but at least the concept is fully designed. In the US, we've been looking at another approach, which is to make basically a LIGO-like detector, but much bigger. that is to make a detector that's 40 kilometers instead of 4 kilometers. You'll remember from Ray's talk that length basically you gain linearly. So if we can make it 40 detectors and do everything else as well, we're 10 times better basically. And this would be then on the Earth's surface, which is cheaper, but we have to worry about the fact that there's Earth's curvature in that length. It has arms that are 40 kilometers and basically would have to have the instrumentation that we use in initial LIGO. This R&D is just starting. It's being led by Matt Evans, who's probably somewhere up here. I can't see him. In developing a group that actually will develop this concept. Over the next few years, we hope to develop both the science priorities so that we know what has to be done, what we want to do, and to begin to do the serious R&D that would go into such detectors. Overall, and this is just a precursor of Kip's talk, the science as we move to the future is going to be very much like what has happened in astronomy. As astronomy started by Galileo looking through a telescope at visible light. We know now we do astronomy by looking at visible light, X-rays, infrared, so forth and so on. The same thing is true here, that we can look at gravitational waves in a particular frequency band on the Earth's surface. It's what's available to us where it's quietest, and that's the audio band. If we want to look at other frequencies, we have to use different methods. The most close to being done, because it's approved and funded, is to do an experiment in space. It's called LISA. It'll move into the frequency band of 10 to the minus 1 to 10 to the minus 4 hertz instead of 10 to 10,000 hertz like ourselves. And that covers a different frequency band. And what's shown above, and I'll leave that to Kip to talk about, is both some of the same phenomenon looked at at earlier time in their evolution and other phenomenon that never reach the frequencies that we get on the Earth. You can look at yet lower frequencies. One concept that's being developed now that I don't have time to talk about is to use timing from radio pulsars. And that's being looked at, looking for signals at very lower frequencies by monitoring the time coming, and we're looking for changes from a set of radio pulsars. And lastly, there are ways to get the effect of gravitational waves from the early universe, which is the most interesting of all in most of our minds, when and if it can be done. And I'll leave it to Ray to talk about those. Thank you.
Thank you very much. And the third presentation will be given by Professor Thorne, who is a theoretician in the field of general relativity. And he has made predictions about the waves created by different astrophysical events and what signals they would be anticipated from these. And as we have heard, he is also one of the pioneers and co-founders of LIGO. So please, Professor Thorne.
Thank you. Can you hear me? I'm so pleased to see so many of my LIGO Virgo colleagues here. I just want to thank you for making me look so good. I really think of myself as more of an icon for this collaboration, and this Nobel Prize is really something that I accept as a representative of you who have made this great success in the end. I would like to highlight the fact that where we are and where we are going in gravitational wave astronomy and physics has relied on three different efforts, each of which was roughly a half a century long, in order to get where we are and where we're going. The first was discussed in considerable detail by Ray Weiss and Barish, the experimental effort, and a little bit along with that, the data analysis effort. I want to talk about the theoretical effort on understanding sources of gravitational waves, the waveforms that are produced, the shapes of the waves produced by these sources, and the information that is carried by those waveforms. Then I want to talk briefly, very briefly, about a third effort that has lasted for about a half a century, a combined theoretical and experimental effort on what is called quantum non-demolition. That's a buzzword, but I'll explain what that buzzword means. Then I will move into the future, focusing on where we might be in the 2030s, the 4 different frequency bands that Barish introduced you to, and then beyond the 2030s. So this is where I'm going in this talk. Let me just look at, just looking at the time here. Okay, so I want to begin, however, with some personal remarks. I was a graduate student at Princeton in the period 1962 to 1965. My thesis advisor was John Archibald Wheeler, a fabulous man who had what seemed at the time wild ideas, most of which have turned out to be true. He was focusing, and he taught me about neutron stars and black holes. But I also was a hanger-on on the fringes of Bob Dickey's experimental gravity research group, of which Ray Weiss at the time was a member. Ray doesn't remember me in graduate school, but I remember him because he was a real intellectual giant in Bob Dickey's group, and I was sort of sitting back there as a mousy theorist trying to understand the experimental side of this subject. But I'm so glad I did, because I learned enough to, in the end, be able to collaborate with Ray Weiss, Ron Drever, Barry Barish. I was also much influenced by Joseph Weber, whom Ray talked about. Joe, I met and spent a lot of time with in the French Alps at a summer school in Les Ouches, near Chamonix. We went hiking in the Alps, and he told me all about his plans and the experimental work that he was already getting going on gravitational wave detection. And so it was quite natural that when I went to Caltech in 1966 as a professor, a young professor, that I would build a theory group that worked in black holes, neutron stars, and the theory of gravitational waves. By 1972, together with colleagues and students, I'd begun to develop some amount of vision for the science that might be done with gravitational waves, the information that might be extracted from gravitational waves. And the key idea was this, in a general form, that there are only 2 kinds of waves that can propagate across the universe, bringing us information about what's very far away. Electromagnetic waves and gravitational waves, and that's it, according to the laws of physics. And there's an enormous difference between the 2 types of waves. Electromagnetic waves are oscillations of the electromagnetic field that propagate through space as time passes. By contrast, gravitational waves are actually oscillations of the fabric or shape of space and time. Extremely different kinds of phenomena. Electromagnetic waves are generally, in astrophysics, incoherent superpositions of emission from individual particles and atoms and molecules, whereas the gravitational waves are produced by the coherent bulk motion of large amounts of mass or energy. Electromagnetic waves are all too easily absorbed and scattered as they travel through the universe, so we only see a small portion of the universe because there's so much obscuration by gas and dust. Whereas gravitational waves are never significantly absorbed or scattered, even if they're emitted near the Big Bang. With those differences, it became quite clear, and I think it was clear to my theorist colleagues and students by 1972, that many sources of gravitational waves will never be seen electromagnetically. And the colliding black holes that we have seen thus far, there's been no electromagnetic signal. That surprises then are likely, and that there is a potential to revolutionize our understanding of the universe using this radically different kind of waves. So that was what we had in mind already by the early 1970s. And that was the same time, 1972, as Ray Weiss, having gone from Princeton back to MIT as a young professor, he wrote a classic paper in which he described the design for an interferometric gravitational wave detector, and he identified all the major noise sources that these kinds of detectors might have to deal with. and how you would deal with each of them, and what kinds of sensitivity you could get as a result. And he concluded that there was a real chance to be able to build detectors that could reach the sensitivities that were required by the sources that my colleagues and I were thinking about. Now, I looked at Ray's ideas, and I stated in a textbook, a classic textbook that I wrote with John Wheeler, my thesis advisor, and Charles Misner, that these are not very promising. I mean, look, he was telling us that you should build a detector that measures the motions of masses with 10 to the minus 12, 1/trillionth of the amplitude of motion compared to the wavelength of the light you're using. You measure a detector that moves by an amount that is 1/1000th the diameter of the nucleus of an atom. And an atom nucleus is 100,000 times smaller than an atom. I mean, it just was crazy. And then I studied his paper, which he didn't publish in the regular literature. He put it in an internal report at MIT because his attitude was, you don't publish something like this until you've detected gravitational waves. But he disseminated it quite widely among his colleagues. I read it, and I began to think, well, maybe this will work. I had this long, all-night discussion with him in Washington, D.C. that he referred to. I had discussions with Vladimir Berginsky in Moscow and later with Ronald Drever, whom we brought to Caltech to start the Caltech effort. I became convinced, and it seemed to me that because the potential of this for human future understanding of the universe is so great, that I should do everything that I could as a theorist to help my experimental colleagues succeed. And so here I am. I and my students, in the end, devoted probably 70% of our research effort from then on to LIGO. Let me now talk about sources of gravitational waves. 1978, we had a workshop on sources of gravitational waves, gathered together essentially all of the theorists and experimenters who at that time were working in the field. Ray Weiss is here, Ron Drever is here, Barish is not here because he hasn't joined into this field yet, although he did play a crucial role in helping us get Caltech into the field behind the scenes on a committee that recommended that we move forward in the field. And at that workshop, at the end, there was a discussion of strengths of sources. And this comes from the paper describing the workshop. Supernovae, where an upper limit was here, that's 10 to the minus 21. This is frequency. This is the strain that we've been talking about. Compact binary mergers, that's black hole binary, two black holes, two neutron stars, a black hole neutron star, estimated to be in this region. And so it seemed clear to us that the top goal had to be to reach a strain sensitivity of 10 to the minus 21. And so we even had T-shirts made up that said 10 to the minus 21 or bust. There is the signal that came in. The first signal was seen 1 times 10 to the minus 21. That's obviously largely luck that we were right on the money. But that was our goal beginning in 1978, and that's where the first signal came. In 1983, when we were planning LIGO, it seemed pretty clear to me that the likely first detection was binary black holes, and this is basically what I argued from then on, though I think most of the community was expecting it to be two neutron stars. But it seemed to me already then that the following would outweigh the neutron stars for the black holes in favor of black holes instead of neutron stars. The distance to which you could see a signal for two objects going around each other is approximately proportional to the masses of the objects. We were thinking at the time that the black holes we would be dealing with were maybe 10 times heavier than neutron stars. So you would see a volume of the universe that would be 1,000 times greater than for neutron stars. And that seemed to me that would outweigh the lower absolute numbers of black holes there are in the universe compared to neutron stars. And that's how it did turn out to be. But we were very uncertain as to how strong these waves were. But we knew it was somewhere in the vicinity of that 10 to the minus 21. Numerical simulations were going to be needed, it seemed very clear to me in that era, in order to be able to extract the information from the colliding black holes that they carry. Because we could not, with pencil and paper and analytical techniques, we could not solve Einstein's equations to compute the shapes of the gravitational waves coming from colliding black holes. And so we had to do it by numerical relativity. So let me go back, a brief history of numerical simulations. This begins in the 1950s, motivated by Johnny Wheeler, my thesis advisor, who told us already in the 1950s that we should try to study the veritable storms in the fabric of space and time that occur when space and time, the geometry of space and time, are highly excited in a nonlinear fashion and rapidly changing. And we had, and he said, you go out and study this thing that I call geometric dynamics. We tried, we fell flat on our faces, we didn't have the tools to do it. But he recognized, and his students around him recognized, that in order to really do this, you had to do it numerically. So you had to begin to build the tools of solving Einstein's equations numerically on a computer or computer simulations. So the foundations were laid in the period from 58 to 64 by Charles Misner and Richard Lindquist, who were associated with Johnny Wheeler, Susan Hahn, who was a computer scientist at IBM, who teamed up with Richard Lindquist to start this out. This is the best photograph I can find of Lindquist in that era. It was not, however, until 1978 the first successful collision simulation was done of head-on collisions of two black holes by Larry Smarr and Kenneth Epley, building on foundations laid by Bryce DeWitt and earlier foundations of Misner, Hahn, and Lindquist. And there are a number of other contributors in this period. I'm highlighting the people who were really the giants in this early era. So here, 58 to 78, this is 20 years already, the struggling to get this started. Next was the problem of doing two black holes that circle around each other and spiral together, collide and merge. And the community began to work on that, and it became a very concerted effort by 1983 when we were co-founding LIGO, and we were telling our colleagues doing these simulations, we really need these simulations in order to extract information from the waves that we will see. By the 1990s, there was something called the Binary Black Hole Grand Challenge Alliance, led by Richard Mantzner at the University of Texas. All of the world's experts in this getting together and working in a concerted sort of a way. And I became a little concerned that it was going more slowly than it should be, so I made a bet. I like to make bets. I made a bet that I hereby wager that LIGO will discover convincing gravitational waves from black hole coalescence or merger before the numerical relativity community has a code capable of computing waveforms. And I wanted to lose this bet in the worst possible way. I wanted to lose this bet. By the early 2000s, I became alarmed. The progress really was slower than the experimental progress. Why was it slow? It's really hard. You're trying to simulate not two things that collide in space and time. You're simulating things that are made out of warped space and time that are colliding. So you don't have an arena in which this is going on. You're simulating the arena itself, a warped arena in which this is going on. And so by the early 2000s, I became alarmed. And so I started, in collaboration with Saul Tukulski at Cornell, what we call the SXS collaboration to work in this field. Saul had been working on this already for a few years. And in 2004, the first successful simulations were done by Franz Pretorius, a postdoc in our group, Joan Centrella, Manuela Campanelli, and their research groups. By 2014, the simulations were mature enough for the first LIGO observations. And I conceded the bet with great happiness. And when the first signal came in September 14, 2015, the numerical relativity gravitational waveform is the red here. The observed waveform is the gray, and that matched beautifully. And by comparing those waves, the theoretical and the observational with each other, we inferred the properties of the black holes and the distance to the sources. You can then go back, knowing from the observations and the comparison of the theoretical waveforms with the observational waveforms, you can go back and look at the simulations and see what was happening during those simulations. And this is a simulation of the colliding black holes as seen from outside our universe, looking in on the warped shape of space and time around the black hole. The red is the slowing of time. The arrows are the dragging of space into motion. It's a gigantic splash in the shape of space and the slowing of time. And then an oscillation, the gravitational waves go propagating out. You can also compute what it would have looked like to your eyes if you had seen the two black holes go around each other, collide and merge, creating what's called gravitational lensing, distorting the star field that's behind the two black holes. And this is a movie that was played extensively at the time of the first discovery that came again from this XSS collaboration. It was essential that we not only have numerical relativity simulations, but for the earlier parts of the waveforms, they were computed by a different technique called post-Newtonian expansion, which I won't go into detail, but that was another 40-year effort led primarily by Luc Blanchet and Thibaut Damour, and then the matching the two together by a different technique led by Thibaut Damour and Alessandro Buonanno. So that was the way we had the waveforms that we needed. Quantum non-demolition, I just want to mention very briefly because I'm also running out of time. The challenge is to monitor the motions of 40-kilogram mirrors to a precision that is 10 to the minus 17 centimeters, which turns out to be approximately the half-width of the quantum mechanical wave function of the center of mass degrees of freedom of these mirrors. So the challenge in advanced LIGO is to deal with quantum fluctuations of the motions of the mirrors themselves to circumvent the Heisenberg uncertainty principle. And this means that for the first time in advanced LIGO, humans see human-sized objects behave quantum mechanically. And that has required developing a field of technology called quantum non-demolition technology to deal with this. This is a branch of modern quantum information science. It was Vladimir Brzezinski in 1968 that told us we needed to do this, no matter what kind of gravity wave detectors we built. I didn't understand what he was saying for 10 years, and then I finally understood. And then I had my research group work as closely as possible with his research group to work out the techniques for this. I'm running out of time. I'm going to skip over my discussion of the techniques for this, except to say that the key idea, which comes primarily from Carlton Caves and from Bill Unruh, is that you take the vacuum of quantum electrodynamics, the vacuum fluctuations of light, and you modify that vacuum by what is called squeezing, and you inject the squeezed vacuum into the back end of the interferometer. It sounds just crazy, but this turns out to be absolutely crucial for the future of this field when we go beyond advanced LIGO. I want to wind up by briefly talking about gravitational wave astronomy in the 2030s. There are 4 different frequency bands that Barish talked about. The low frequency band, minutes to hours, to be studied by LISA, these 3 spacecraft that track each other with laser beams. It's a ESA mission. We hope that it launches by about 2030. And LISA is capable of monitoring the gravitational waves from giant black holes, millions of suns that spiral around each other, collide and merge with signal-to-noise ratios of 10,000 or more, and thereby capable of studying geometric dynamics with unbelievably high precision. Pulsar timing arrays, a gravitational wave sweeps across the Earth, and it speeds up or slows down all the clocks on the Earth. And so naturally, if you time pulsars at different locations on the sky, they will all slow down and speed up, or appear to slow down and speed up in synchrony, because it's the clocks on the Earth that are being screwed up. And that technique we'll look at supergiant black holes, billions of suns in mass. So we cover the whole range from solar mass scale of black holes to millions of solar masses to billions of solar masses. And a small black hole orbiting around a large black hole generates gravitational waves that carry a full map of the large black hole that is being explored by the small black hole as the small black hole goes around it in orbit. And here's the small black hole going around the large black hole. The orbit is wildly crazy because of the dragging of space into motion by the big black hole, as well as other relativistic effects. And it samples essentially the entire space around the big black hole and gives us then the information to do exquisitely accurate mapping of the geometry of space and time around big black holes. What are the central bodies not a black hole? For example, the naked singularity, the orbits will be wildly different and the maps will be wildly different. So we have the capability to search for unexpected kinds of massive central bodies. I want to wind up by saying that we have the potential to study the earliest moments of the universe by the 2030s. When the universe was at an age of 10 to the minus 12 seconds, there is predicted to have been an electroweak phase transition where the electromagnetic force and the weak force come apart and gain their own individual identities, the birth of the laws of electromagnetism. And this may have occurred in what's called a first-order phase transition inside bubbles, the bubbles of the new phase where electromagnetic force does exist. In the bulk of the old phase where it doesn't exist, collide, produce gravitational waves, which today have been redshifted into LISA's frequency band. And Ligo could see similar phase transitions that would have occurred when the universe was 10 to the minus 22 seconds old, but we have no idea what was going on in the universe at age 10 to the minus 22 seconds. Primordial gravitational waves coming off of the Big Bang itself are predicted to have been amplified, whatever came off the Big Bang, amplified by inflation in the first 10 to the minus 33 seconds of the universe. Theoretical prediction that is pretty strongly believed by theoretical physicists. And what is speculated to come off the Big Bang is vacuum fluctuations, the minimum amount of fluctuations of the gravitational field that are possible. They would get amplified to make a rather rich spectrum of real gravitational waves that would propagate out, interact with a hot plasma when the universe is 380,000 years old, and put a polarization on the cosmic microwave background produced by the hot electrons at that age, which would be seen today. And so the challenge of the people who work with the cosmic microwave background is to measure definitively that polarization, thereby infer the gravitational waves that came off the Big Bang, convolved with the effects of inflation. So the spectrum that would be seen is a combination of the effects of inflation and what came off the Big Bang. We also have the potential by 2050 to fly a successor to the LISA mission, which would be capable of seeing these gravitational waves from the earliest moments of the universe independently at periods of a few seconds. So imagine if you have the gravitational waves with periods of a few seconds. You have the primordial gravitational waves with periods of 100 million years seen by polarization on the sky, polarization pattern on the sky. Both of them are produced by whatever came off the Big Bang convolved with the effects of inflation. And I envision that by the 2050s, those will not agree. There will not be an agreement between what's coming off at periods of a few seconds, at periods of 100 million years. And there will be a huge mystery. What really came off the Big Bang? Why was it not vacuum fluctuation? So that's my dream of the future. And that at that point, those observations may really feed into understanding the laws of quantum gravity that govern the birth of the universe. So let me just conclude by saying, it was 400 years ago that Galileo created modern electromagnetic astronomy by turning a small optical telescope on the sky and discovering the moons of Jupiter. It was 2 years ago that this wonderful LIGO-Virgo collaboration turned on the advanced detectors, the advanced LIGO detectors, and saw the gravitational waves from collisions of two black holes. In those 400 years since Galileo, we have learned so much about the universe with optical astronomy. Our understanding of the universe is so different today than it was 400 years ago, thanks to optical astronomy. What might be the future 400 years from now when we have 400 years in our pockets of gravitational astronomy together with electromagnetic astronomy? I think the future is really very, very exciting. Thank you.
So I would now ask Professor Weiss and Professor Barish. So if you go over to the far in the front of the stage, so you can advance a little. So, okay, get over there. Okay.